Welcome everyone to the STAC and Cloud Optimized Data session. I am Annie Burgess. I'm the lab director for the Earth Science Information Partners. Just a quick intro. So I'm kind of like the room host for this meeting. I'll pass it over to the session organizers soon. So everyone knows that we're using Zoom for this meeting. I'd encourage you to familiarize yourself with the kind of the bar at the bottom where they have reactions and hand raise options. Also, just so we can be collegial with each other, if your name on the right isn't totally obvious as to what your name is, if you could kind of hover over your name and use more and change your name to something that you could be referred to so we know how to say your name if we're responding to a question. Thanks, Ed. Also, if you'd like to put in chat your name and your affiliation, just as a way to say hi to your colleagues on the line and we can get a sense of who's in the room, that would be great. So again, that's in the Zoom chat. Go ahead and introduce yourself. As a reminder, please mute yourself when you're not speaking. We'd like to have cameras on during the discussion portion of the session, but you could turn your cameras off when a speaker is presenting their slides and sharing screen. A reminder to look in Slack, or not in Slack, but in Sketch at our community participation guidelines. And let me make sure I got everything. Yeah, I think that's about it. Oh, last thing I wanted to mention is, so because this is, we have a couple ways you can provide feedback. In the Kiko chat space for this session, you can see a notes page, and there's also a word that says Slido. Probably everyone has used Slido at this point. But Slido is where we'd like you to ask questions during the session. Slido is a good feature of upvoting questions. So if people feel they have a similar question. So again, you can find that in the Kiko chat space called Slido. And you can see Rich has said, is this the right place to ask a question? And I'm going to give that an upvote. So please go ahead and poke around in there and ask questions during our presentations. Does anyone have any questions about the tech before we get going? Great. If not, I will hand it over to your session organizer, Matt Hansen, to get things going.
Okay, thank you, Annie. Hello, everyone. Let me share my screen if I can find it again. Okay, can everybody see that? And then is it in presenter mode here? Okay, so the URL that Rich kindly made here, there's a tiny URL there that will take you straight to the right page, because I know that it was a little confusing trying to find the right page. So if you're watching on YouTube, you could follow that and click on the link to join via Zoom. That's also where you can ask questions in the chat app. Today I'm going to be, so this session is on STAC and COGS, although it's really more on COGS. A couple of the talks don't necessarily talk about STAC per se, but the overall concept here is that we're talking about how better to use, discover, and analyze data that is in the cloud. I will be giving a short introduction on STAC in case anybody is not quite familiar with what it is, and a project that we have done recently on creating COGS of Sentinel-2 level 2 data. So first, I'd like to talk just briefly about Digital Earth Africa, and I should totally have quieted Slack because it's going to bug me now for a long time. 1 sec, please. Okay. So the project is Digital Earth Africa. Digital Earth Africa is funded by actually the Australian government, Geoscience Australia, and it's data that's hosted in Africa that is continent-wide And it's really supposed to be a comprehensive set of remote sensing analysis ready data to help address the challenges of sustainable development within Africa. The Digital Earth Africa project arose after Digital Earth Australia, which saw the development of a Python library and suite of tools called Open Data Cube. Open Data Cube is a way to index and create multi-dimensional time series and data cubes for out of really any sort of remote sensing data. And it's outside the scope of this talk to talk about it, but I just wanted to mention it because this is how Geoscience Australia and the Digital Earth Africa project is using this data. It's not one of the only ways to use this data. Scott Henderson will be talking later about other ways to also use STAC and COGS. So the goal of this project was to get some analysis ready data that was Sentinel-2. Sentinel-2 is a extremely valuable set of data. Sentinel-2A and 2B are two different platforms. The last one was launched in 2017, although due to some early issues with some of the metadata, the level 2 version of the data actually doesn't really go past the beginning of 2017, I believe. But Sentinel-2 has been proven to be a very valuable data set. It's many of the bands are higher resolution than Landsat. It's comparable. It doesn't have long wave infrared bands, but it does have some extra small narrow band vegetation bands that have proven to be fairly useful. So the Amazon Public Datasets program has several sets of these high value data sets, which has proven to be very valuable for AWS, because if they take data and put it on and make it available for free, then folks will use their computing resources in order to actually access that data. So Sentinel-2 is one of these data sets. It has been put on there by Synergize. There are two different data products. There's the level 1C and the level 2A. So level 2A is what people might call analysis ready data. It's surface reflectance data. And it's for most applications, that's really what it is that you want to use. For quite a while, level 1C was the only data that was available on AWS, but it was actually the Digital Earth Africa and Geoscience Australia that really prompted and really pushed forward a lot of the processing of the level 2 data for surface reflectance. So now most of the historical archive in Africa has been processed to level 2, but there is actually global data getting processed as well. And it might actually be almost done. So the issue with the Amazon Public Datasets, however, is that it's really hard to find the data that you're interested in. There's no index, there's no way to search. So here, there's you just get a directory listing and you can see all these files. So fortunately, they're organized by grid. And so given an AOI, if you know the grid that you want, you can formulate what the file name should be and you can access the data that way. However, the tile geometry is sometimes different than the actual data geometry. A swath might cut a tile down the middle, so your AOI might fall well outside of the actual data range. And so it's really not ideal. And it's also extremely slow having to search and look through a Amazon bucket. You can use inventory files that make things a little bit easier, but really what we want is not only a way to better find data based on geometries, but also be able to search on arbitrary fields such as cloud cover, the date range, solar angles, specific resolution. So thus we have STAC. So STAC is a emerging community standard that started a couple years ago to try and make one consistent way for people to be able to find geospatial data. These are all different geospatial portals. To date, If you want data from multiple portals, you have to go through each one of them. They each work a little bit differently, and they all have APIs usually backing them. And then there, the situation is even worse. Different fields, cloud cover might be called max cloud cover with one data provider. It might be called cloud_coverage. It might be a percentage. It might be a floating point. There's no consistency there. And so you really need a different client or different drivers to access each one of these APIs and get to that data. So I left in a lot of these slides, but I really want to skip over kind of a lot of this core STAC stuff because I want to get into the more interesting Sentinel-2 data here. But the way that the STAC development process has worked has been an early focus on implementations of catalogs of software. And so we recently released the beta 1 of STAC 1.0, but we actually have a fairly rich and wide ecosystem of software tools that can already be used with it, even though some of them may be a little bit out of date. Currently, the community is working on getting these all up to date to the 1.0 standard. STAC is, the focus here is on simple discovery, and not to just be replacing all existing metadata. This isn't a new standard that is intended to replace something else. This really is a standard for which there wasn't anything before. It's a way to harmonize the search and discovery of this data for users, not for the data providers themselves. And there's been a lot of input and from different data providers through this process over the last couple of years. And you can go to the stacspec.org website. STAC is all JSON. There's 3 different entities in STAC. There's collections, catalogs, and items. Again, I'm going to skip over these. You can look at the website, you can look at these slides and sort of get a sense for the fields and what's there, but you see it's really not there. It's mostly human readable. That's also by design. We want users to be able to look at a catalog, look at a collection, and be able to understand what it is that they're looking for. STAC catalogs also have linked relationships between each other so that they can be crawled. So you could have a static STAC catalog that could be indexed, that could be crawled and indexed into something like an Elasticsearch backend or PostGIS backend so that it's more easily searchable, but you don't actually need to stand up any external service in order to take advantage of STAC. You might have a UAV data set that's mostly archival purposes, and you could have all that STAC metadata alongside there ready to be ingested and crawled if you need it at a later date. A STAC item is GeoJSON, which makes it very nice because the output from any of these tools that output results will can be opened immediately up in geojson.io or QGIS. There's a handful of core properties. Most importantly, you have the date time. You have some platform information if it's applicable. You can look at the full list on the site. And what is of most use is the actual assets. So you have an item that represents a scene or a region for a certain date time, and the assets are the individual data files. So, and STAC item could have one or more. Use of a thumbnail is strongly encouraged. There might be a preview image, and then you might have individual data files. You also, in most cases, will also have additional metadata. So the original metadata for the item, that's an asset as well. STAC is extensible. There's a variety of content extensions. I'm not going to talk about any of these. Just wanted to show that there are, for different types of data, there has been some attempts and efforts to make extensions for those, such as the DataCube extension or point cloud extension. The most common one is the EO extension and the SAR extension. For Sentinel-2, we use 4 different extensions. We use the EO extension, the satellite, the view geometry, and projection. The electrical optical extension allows you to specify spectral band information and the cloud cover. It specifies the band information through the use of this bands object, where you can get the center wavelength, and really most importantly is this common name. So we have in the spec, we came up with a list of common spectral bands that could be used. The idea here is that all blue bands are roughly going to be the same. This doesn't say that the spectral characteristics of those bands are exactly the same. It just means that there's a blue band. If you have a short wave band, though, that is going to be in one of those 2 atmospheric windows at 1.6 or 2.2 microns. So you can name it as such. It doesn't imply that it's a specific width at all.
Hey, Matt.
Yes.
You're at 12 minutes. I just wanted to give you a time check.
12 minutes in or 12 minutes left?
12 minutes in.
All right. All right, good to know. Thanks. So the satellites, so the first table here is the satellite extension. So this gives us orbital state, which is useful for SAR. It's not so useful for Sentinel-2. The orbital state in the relative orbit is more useful for SAR instruments, but we do use it to specify the ascending or descending orbit here. And then the view geometry, these are all optional fields. You might not use all of them. In the case of Sentinel, off nadir is always 0 because it's a non-tasking satellite, but we include the sun azimuth and sun elevation angles here. And I believe the azimuth as well, but not the incidence angle, which can be derived from the off nadir. So now the projection extension is a little bit different than some of these other extensions, because all the fields that I have mentioned so far, really the focus is on that discoverability piece. I want to find data that has a low cloud cover. I want data of these bands. I want data that has a certain sun azimuth angle because I want my target illuminated from some direction, let's say. The projection extension is focused on usage. You're not searching on these fields. It's a way to take some more detailed technical information from the data files, such as the projection information and the geo-transform of that. So you actually have the affine transformation, and taking that and putting it into the metadata. The reason for doing this is because I previously mentioned Open Data Cube in Geoscience Australia. This was really a request from them, and we worked with them on making this extension to include the information that they needed. They can now crawl that catalog and they can get out that geo-transform information and they can put it into Open Data Cube without having to touch any data file. And this is really important because before, for every scene, they had to go and touch 4 different data files for the 4 different resolutions that they had. Each one had a slightly different transform. So STAC is also an API. It's based on the OGC API features. There's a few additional endpoints. There's a catalog, which represents a STAC catalog. There's also a search endpoint, which allows you to do cross-collection search. So in STAC, we have collections. Landsat 8 could be a collection. Sentinel-2 might be a collection. And the /search endpoint allows you to search across all of these. The core OGC API features did not allow for cross-collection search. Thus, we had to add on to it for STAC. There's actually the cross-collection search, and then there's a search endpoint for each collection as well. That's part of the core OGC standard. So I wanted to explore STAC here just a little bit. So this is actually the current catalog that is up and running. So if you were to go to that URL, install JSON viewer or some sort of like nice little JSON formatter in your browser. So here's our root STAC catalog. It's got a description, it's got the STAC version. We also have collections. Every child is a collection. As part of this effort, I had to index the existing level 1C and level 2A files. And then we have our cogs here. So we can go to any one of these. This is our collection level metadata. All right, so we have provider information. We have information on what types of assets would be in any individual asset underneath it. We have this spectral band information showing you which assets are going to have which bands. And if we go all the way down to the bottom, we have these links so that we can actually go back to the root catalog or so on. In the, hold on. If we go to items, so this is a search endpoint. So here you can see we have 1.4 million scenes here. It just returns the first 10. And this is this is a GeoJSON feature collection. And here we actually have the geometry, we have our properties, and we have our assets. And these are the actual files. So if we go to preview, here's a super nice Sentinel-2 image. Okay, so let me go back to presenter mode here. Okay, am I back in presenter mode, does it look like? I feel like I can see anything anymore.
Yeah.
Okay.
You're at 17 minutes.
Okay, great. So, so this is the search API endpoint, or search.aws. Our goal here is to try and add in more STAC catalogs for other Amazon public data sets, so that there is an easier way to search. Right now, as you saw, there's the Sentinel-2 collections. I do have a section here, but I don't think I have time to talk about cloud-friendly formats, but that's okay because other people will be talking about COGS. I'm going to skip ahead and just talk about the effort, or just some background. The Sentinel-2 data in those level 1 and level 2 files originally are in a JPEG, open JPEG 2000 format. For a variety of reasons, this isn't really conducive to a lot of scaling. The open source JPEG 2000 drivers tend to be very slow. There's issues with how many times they access the data file, which can lead to an unexpected expense. You can read Vincent Sorrego's blog post on that from a couple of years ago. It's a fun read. And so that's why Geoscience Australia for the DE Africa project wanted to convert these into the cloud optimized GeoTIFFs. So of the 9.4 million scenes, I ended up indexing all of those into the STAC catalog and then taking just Africa and converting those into COGS. Now, before somebody asks, yes, we do have a plan for turning the entire global archive into COGS in the coming months. So right now we do have all of Africa there. That's the 1.4 million. And this slide here shows how you can use sat search and sat fetch to search. You can install that. It's a pip installable library. Here's a little animated GIF showing use of it at the command line. So here I'm searching for what intersects with the state of Maine between two dates, and print a little calendar, terminal calendar. I'm going to narrow it down more and look for just the scenes that have low cloud cover, and I'll look at those. I have 42 different dates there. Now I decided I actually want just Landsat. And so let's see what that shows. I've got 8 final dates here. I can save this. It'll save it as a GeoJSON feature collection file, which I can then open up and I can look at where those footprints are later. Ngorongoro crater in northern Tanzania is shown on as a red polygon. The purple is a Sentinel-2 footprint. Landsat is shown in the green footprint. So here, using sat search, find 18 different Landsat scenes. And I can use sat fetch to actually just fetch just the red, green, and blue bands and stack those into and clip those into individual RGB files. each Landsat scene, if you go to the original source, those are a gigabyte a piece. So downloading 18 of the scenes for just the areas of interest in less than a minute is a pretty good improvement there. This is really just to show what is possible when this data is in a cloud optimized format. And we can do the same thing for Sentinel now as well. That's all I got. Any questions?
Looks like, Matt, can you hear me? This is Annie.
Yes.
We've got one from Slido that asked, what is the latency and data available on AWS versus STAC, say, for example, for Sentinel-2?
Okay, so like how long before it's available?
Yeah.
Okay, so Synergize is the one that puts the Sentinel-2 data into this will cover some details that I didn't actually mention. So that data is all in EU Central region. And they send off an SNS topic every time a new scene gets published. So presumably that is right away. They'll publish that topic. So we actually have a queue that subscribes to that. And so as soon as it's available on AWS, it gets added to our queue for processing. So it should be within 10 minutes. I think at the height, I was processing 60,000 cogs per hour. So there's not really, and that was doing historical processing. New scenes don't even approach that. So it would probably be done within about 10 minutes. It's copied into, it's put into US West 2. And it's free. It's not a requester pays bucket like the original either. So these are not only cogs, but they're completely free. And the plan, which I think is starting, is that Digital Earth Africa, that data is actually going to be copied and mirrored in the new Cape Town region. So it will exist in both. So globally, it will exist in US West. And for Africa, it'll exist in Cape Town as well.
Thanks, Matt. For the sake of time, I think we're going to move on to our next speaker, but people can keep adding those questions to Slido, and Matt can keep an eye on that as well and answer them while we've got our next speaker coming up. But let's see, Rachel, do you want to unmute?
Yep.
I see you there, Rachel. Okay, Rachel, do you want to share your screen?
Absolutely. All right, can folks see that?
You bet.
The screen, great. Okay. All right, so then, hey folks, I know my name is Rachel Wegener and I work for Development Seed, but what we're gonna talk today about is an effort or a project that I worked on that was a collaborative effort between Development Seed and NASA to convert a good chunk of data into cloud optimized GeoTIFF format. So I'll go through and just for about 10, 12 minutes to leave a little bit of time for questions, talk about sort of what we did and why we did it, and also some of the decisions that we had hit as we moved through that process, decisions made in that process. So the project in and of itself was relatively straightforward. We had 3 different NASA data sets, and we wanted to convert them from their original file format into cloud optimized GeoTIFFs. Once we did that, we made the data available through the Public Datasets program. And all of this, the driver behind this was for the NASA Space Apps Challenge. This year focused on a virtual hackathon that was focused on solving problems and challenges related to using NASA Earth data, in particular this year with a focus on COVID-19. To be specific about the data that we converted, we had 1 data set that came from the OMI instrument, looking at that was a nitrogen dioxide, as well as 2 data products from MODIS, aerosol optical depth, and then 2 vegetation indices, NDVI and EVI. And we converted all of those into COG, or Cloud Optimized GeoTIFF, COG. There's benefits of COG, and I think other folks, it looks like, and additional presenters will also be focusing perhaps on the benefits that they had in COGs in their particular projects. For this project, there was three main things that we were excited about. The first and the largest is really the ability of COG to look at a particular area. So even if your data set is completely global, what COGs really excel at is finding a subset of data and just pulling that chunk out without having to need to access all of the rest of the data. If you're looking at web visualization, there's also additional benefits that include things like faster loading times because of a mechanism called overviews, as well as the ability to create these color scales on the fly and update those in the browser. So to look at what that looks like, this is a GIF showing, if you open up, this is one of the data sets, the NDVI data set. And when you start, it's focused on a global view. So all of the data over the entire globe. And it loads relatively quickly. And the reason for that is because we're actually viewing a lower spatial resolution version of the data set. It's part of the overview. And then as we zoom in, we can see that it's a lower spatial resolution as it gets fuzzy right there. And then watch as it updates and renders the higher resolution version, but it only loads the higher resolution version over this particular part of South America. So that's how the loads are able to continue happening rather quickly. So that's the overview feature or piece of Cloud Optimized GeoTIFF. The dynamic color scaling piece is connected to the overview as well as the internal tiling component of COG. So in here, what's happening here is that we are changing the color scale changing this color scale as we choose a new one. This is different from the traditional or historic way of rendering data on the web, where you have to produce these PNGs and the PNG images are uploaded, and that's the color scale that you have. With COGs, because the processing can happen so much faster, you are able to apply a different color scale or a unique color scale as you render. So those are sort of, in and of itself, the project was relatively straightforward in that sense. If you have your data, we had it in one file format, we transformed it into our second data format. As we went through and did that, though, we did keep hitting up against these assumptions that we made about the end users and the needs of the end users that influenced how we approached the data and decisions we made in processing those data sets, all connected to things about data type, file types, and data search, such as issues of STAC. So when we thought about who we were building for, we identified our users to be this group of folks that wants to access the data, that are willing to access from the cloud, that are interested in a particular region, and that have an interest in some way of visualizing the data. And so by thinking about our users in this sense, we really did the conclusion of COG really derives of converting to Cloud Optimized GeoTIFF to derives that these are things that a Cloud Optimized GeoTIFF does particularly well. While we were working, we also had the fortune of working with some science teams connected to these data products at NASA. And so including that really helped make some of the decisions about both doing quality control and checking for completeness, and also giving us context about the scientific data sets that we were processing. So some of these decisions, or how we approached some of these things. Decisions with the science team included things about how much data we should process, what section of the nitrogen dioxide record. And nitrogen dioxide is a relatively short-lived molecule, I suppose. So while the original Space Apps initiative just was pushing for perhaps 2 years of data, we ended up processing more than that in order to keep the data, to make the data as useful as possible, to be able to allow folks to look at a larger historic record. There was also the potential of removing some of the data. So in an effort to make it more analysis ready, to take out some of the values that didn't make a lot of intuitive sense. But we ended up choosing to keep those because of the science team noting that it would, when you remove some data, you're inducing some bias in the data set. And we also chose to include only a couple of variables. So we basically, for each of these data sets, just had 1 to 2 variables. And those came in as different bands in our COG. We also had to make a decision about the scale factor. And so the trade-off here is the decision between, do we want a scale factor, in which case we're closer to analysis ready, but the file is much larger, or do we not want a scale factor, apply the scale factor, in which case we can keep the file smaller, but the user needs to somehow know about that scale factor. In the end, we did decide to apply it, which certainly increased the size of our file. We had to go from an integer to a float, and considered moving down to a 16-bit float, which would have kept the file smaller, but would have lost some precision. So all these part of the sort of analysis-ready data paradigm of considering how we present data. One thing I enjoyed thinking about in terms of this decision was the connection between the data that we're producing and how the data gets discovered. So in this case, metadata can be attached to the particular file. And so that is certainly one way to convey the scale factor. But presumably people aren't going to come into this data by just a friend sending a link or finding something on the internet and going to that without any context. That will be searched through a STAC catalog or through the public datasets program. And so this is another place where the scale factor and the searching and metadata can come into play. There's a couple other decisions that we made for NDVI and the vegetation indices, the NDVI and EVI products. One of them was we took each of the individual MODIS tiles and we aggregated them into a global image. So the MODIS tiles, for folks who may not be familiar, are that they're delivered in terms of not in a global data set, but in these tiles, as in this image throughout the world. So when you find a particular, that's good because I guess it keeps the data small in these bite-sized, so to speak, chunks, approachable, hopefully. But the downside is that if you want, depending on, you have to know, I guess, the particulars of the exact location you want in order to know which file you want, because you have to find that particular tile. So we made the decision to aggregate them into a single image. Now this made the image fairly large. And so that made it harder if you were looking at a user who wanted to download a file. That might be a downside. The image is larger, it takes longer to download. But we are assuming or trying to, we're moving in the direction of catering towards users that are willing and want to access data through the cloud. In that case, as with the COG, the larger data file format, the larger data set isn't an issue because no matter how much data is included in that file, the chunk you're accessing determines how large it is. You don't need to access the entire file or don't download the entire file in order to get to that chunk. We also made a decision in terms of skimming over, there's just multiple orbits that pass over a particular tile. And so when we chose data from each tile, we chose the best orbit effectively for each tile. So I guess to recap, the main things is we had this project where we started with some data and we converted it to COG. And we did that because we were thinking about a particular user that can access their data from the cloud, that's interested in a region and is interested in data visualization. COGs really excel in these areas. We made decisions as we did that, and they suited the needs of our end users, and those decisions included things like data types. So, that's all I have. Thanks, folks, and I can check out questions.
Awesome. Thanks, Rachel.
Yeah.
Let's see. Does anyone have a question? We don't always have to go to Slido. Does anyone have a question for Rachel? Feel free to just unmute and speak up as well.
Hi, this is Chris Linus from NASA. I did have a question about the aggregation that you used to make overlays for the NDVI. Did you use averaging for that, or did you consider the possibility of going with like maximum value for agricultural users?
You mean in terms of selecting the best orbit?
Well, in terms of selecting the best pixel when you make the lower resolution overlays.
Oh, sure. Yeah, we didn't think about anything in that realm, but that would have certainly been that could have been a great addition to the project.
Thanks.
Thanks, Chris. And oh, go ahead.
I had a question. Hi. So Jim Frew, UC Santa Barbara. That last example you gave was interesting. So if I understand you correctly, you basically made the mother of all geotiffs out of all of the MODIS tiles. Is that correct?
Yep, global TIFF.
You mean like one massive image, which nobody was going to download. Everybody was going to access a subset of it. So given that there was going to be an API sitting on top of this thing, did you bake off this idea of one gigantic image against other representations that provide a service-based access to image data? My question is I can see why some people might want to get a GeoTIFF, but since this is a gigantic GeoTIFF that you're not going to give to anybody unless they're a masochist, I mean, then presumably, you know, there's other ways to support an API-based access to that kind of imagery. So I'd be interested how that compared against using this cloud-optimized GeoTIFF.
Sure. If I'm understanding, the API access for the GeoTIFF, I think part of, I think the hope with the cloud optimized GeoTIFF is that whatever API is being used allows you to access a particular piece of that data set and not need to access the entire thing at once, because that's where the COG really comes in and has a great benefit.
Yeah, Rachel, I could step in here too and say, this is Amy. I'm also at Development Seed. And basically for this particular data set, I think we sort of made a decision for the user that it would be easiest to just have a global representation of the data and balance that against the option, which I think you're mentioning, which is like basically building additional services using something like, you know, maybe some of y'all have heard of like Mosaic JSON, where you might actually be composing a global, global representation just using sort of a metadata file, but actually storing the cloud optimized GeoTIFFs in separate files, depending maybe based on the granular, maybe based off of some other region that you've defined. For this particular, you know, COVID Space Apps challenge and data set, we went with an approach that sort of required the least onboarding, I guess, for the user to learn additional tools to work with that data.
This is Rich, and I think the really exciting thing here about, you know, these cloud optimized data analysis ready data is you don't need a data service. You know, you don't have to depend on somebody's awesome service. You can just go right to the data. You know, that's what that's what she showed here. That's cool.
I had a question on Slido, but I'll ask anyway. So, is there a benefit to saving data in like in cloud optimized GeoTIFF if you're, let's say, working on HPC or locally on your machine, or is there some price you pay now versus regular TIFF?
I mean, so if you're working locally and you have a cloud optimized GeoTIFF, you still have the tiling benefit, or if you got that large TIFF onto your computer, you wouldn't, and it was some, maybe you only have 16 gigabytes of RAM or something, and you don't have to open the entire thing still. So you still have the ability to go to the particular window that you're looking for. It's just that particular feature, I think it's talked about in a cloud format because it works particularly well as to when you're sending data requests over a network. The requests are much more manageable when they're tinier, but on your local machine, it works in the same or similar way.
So basically it's good to start using COG. I guess that was my question.
That's what I'd say.
Yeah, thank you.
All right, thanks, Rachel. Let's see, who is the next speaker?
That's me, I believe.
Yep, Kyle.
Let's see. Can you see my screen?
Yep.
Yes.
Okay. So I'm Kyle. I'm excited to talk to you today about recent projects I've been doing that use cloud optimized GeoTIFFs to bring them into the browser to enable new methods in web mapping. So first, I'll give a quick overview of why I'm excited about cloud optimized GeoTIFFs, followed by applications that I've built with them and in-depth details for working with them yourself. So why am I so excited about cloud optimized GeoTIFF? Well, as we've seen in the previous talks, cloud optimized GeoTIFFs support efficient data streaming. This means that you can have a function, some compute that takes your cloud optimized GeoTIFF data and combines it on the fly into image tiles that you send to a web browser. This is exciting because there's huge collections of data that are publicly available in cloud optimized GeoTIFF. So you have Landsat 8, you have Sentinel-2, you have elevation data, and all of this is accessible. So I believe that the browser is the future of geospatial data visualization. But the big question there is, how do you move the data to the browser? You have terabytes, even petabytes of data in the cloud, and you can't ask somebody when they visit your website to download that much data. So you could request these files directly from the browser, but there's latency every time you request a file from S3. And so I found that having some compute, I use AWS Lambda in the middle, means that you can combine these cloud optimized GeoTIFFs and reproject them into one image that is ready for use in the browser. So the first project that to talk about is USGS topographic maps. I found that there's 180,000 USGS topographic maps between 1884 and 2006, which were digitized and put into cloud optimized GeoTIFF format. This means that you can have an interactive web map of all of these files that is seamless, and you see all the different maps as you zoom around. Here I'm removing the map collar on the fly. So on the bottom left, you can see that here's a map of Alaska, and every map has this metadata that's human readable on the outside. So on the fly, I cut that away so that, as you see on the top right, there's no collar in between the different files. The next data source that I worked with is elevation data. As of this spring, USGS has all of their data in cloud optimized GeoTIFF format. This is really exciting because USGS is taking 1 meter resolution elevation data of the US and hopes to have that ready by 2023. So you can start using this in cloud optimized GeoTIFF format. And as new data becomes available, you can update with new regions of the US that have high resolution data. There's multiple things that you can make. So for example, I made server side Python libraries to create a terrain mesh out of this data. So here, this demo is actually using AWS terrain tiles, which is a little bit faster and easy to work with, but there's no reason why it can't use cloud optimized GeoTIFF. Another project I've worked with is NAIP imagery. This is exciting because it's imagery that's high resolution and taken by the US Department of Agriculture. From 2011 to 2018, that data is in a public S3 bucket. And it's a 3-year repeat cycle. So most states, images are taken at the state level, and most states have 3 to 4 years in cloud optimized GeoTIFF format. For future work, as of last month, 4-band imagery that includes a 4th near infrared band is also in cloud optimized GeoTIFF format. So you could do stuff like vegetation analysis with this data. And the exciting thing is that you can combine these different sources. Here's the NAIP imagery combined with the elevation data that I showed earlier, where you're combining each of these cloud optimized GeoTIFF formats into one thing in the browser. And this demo doesn't depend on any external data other than the data coming from cloud optimized GeoTIFFs. But the project that I've worked the most on over the last 5 months is Landsat. Landsat's amazing because it's been around since 1972, and there is a continuous stream of data. It has 16-day repeat cycle and relatively high 30-meter spectral resolution. As of later this year, the Landsat Collection 2, a major reprocessing of the entire Landsat archive, will be in cloud optimized GeoTIFF format. So you can have all of the data since 1972 at your access. I want to talk a little bit about how I'm using this Landsat data and how it's different from existing approaches. That the existing approaches generally are the left side. You have server-side rendering, where say you want to display a true color image of Landsat. Well, your serverless function, or whatever your compute is, has to grab the red, green, and blue bands from the open data bucket and combine them into one image that you send to the browser. My approach is different. I'm parallelizing this process by requesting the red, green, and blue bands individually and combining them on the browser in the GPU. So this is fast because you're able to parallelize this process. but it also provides more benefits. That say you have your red, green, and blue image, true color image, but you additionally want to apply pan sharpening. So I implemented code to do pan sharpening in the GPU in the browser. This means that if you were previously looking at the true color image, and then you wanted to add pan sharpening, you don't need to ask the server for a new full image. That previously you would have to ask the server for a pan sharpened image that has the red, green, and blue. The server has to refetch those red, green, and blue bands and then add them to the new panchromatic band. But since I'm downloading each band individually, the red, green, and blue bands are already cached in the browser. So I only have to download the new panchromatic band, which makes it faster and cheaper, and then apply pan sharpening in the GPU in the browser. So this approach of downloading bands individually opens up tons of new opportunities. For example, it's really easy to have false color images. Here, if you were looking, this is a false color infrared image of Landsat 8 imagery in the Nile River Delta. That if you were previously looking at this in true color, the 4, 3, and 2 indexed bands would have been downloaded. And then if you want to change to false color, your browser only has to download one new set of bands. It only has to download that 5 band and then can combine those in the browser into this false color image, which makes it faster because you only need to download those new bands. But you can't, this opens up more opportunities than just false color images. Here, this is the same place, but with a spectral index. Here it's NDVI, Normalized Difference Vegetation Index. And if you switch to this from the previous image, no new data is downloaded. The NDVI uses the 4 and 5 bands. So it's able to take that data that's already in the browser and combine it into a spectral index, and then apply this color map. So the index creates values from -1 to 1. You can apply this color map, which is applied on the GPU, so it's really fast. And it means that you can change color maps on the fly, and you don't need to download any new data. This is really extensible for new algorithms because anything that you want to do, especially that operates on pixel by pixel, is really easy to implement on the GPU. And it's kind of wasteful to be doing this server side when GPUs are incredibly efficient at doing this sort of image analysis, and basic remote sensing analysis like NDVI or Enhanced Vegetation Index, EVI, is really easy to do in the GPU. Another thing that working with this cloud optimized geotiff data allows you to do is it gives you really great flexibility of the images that you choose. So for here, I'm looking at the Northern Oregon, where there's the Eagle Creek fire in late summer 2017. And because I'm not pre-generating and storing any data, I have the flexibility to look at the area in summer 2017 before the fire, and then look again in fall 2017 after the fire. And you can see how strong that burn scar is. And of course, you can put that all together. You can combine the terrain and the ability to do band computations on the GPU and the color map into one thing. That here is the NDVI of Landsat over the Grand Canyon. And adding this third dimension is really exciting because you can see the higher elevations. The Kaibab Plateau is able to collect this, is at higher elevations and is able to collect more water and is able to support higher images, or sorry, higher vegetation. And with this third dimension, it's cool to see that in the side canyons, they're able to collect water because of their shape. You see more vegetation. So I've talked about how, and I've talked about the what, but not the why. How did I get involved in this project, and why have I been so excited about Cloud Optimized GeoTIFF? So 5 months ago, when I started these projects, I was unemployed. I was teaching myself software engineering and excited to work with remote sensing. Satellite imagery is really cool, but historically, you need so much capital to work with satellite data. If you wanted to do a map of the globe with Landsat data, you'd have to download Landsat data for the entire globe. You'd have to compute to convert that into tiles that the browser is expecting. And then you have to store that. And just storing a single set of Landsat images to cover the globe would be hundreds of dollars a month. So I'm excited about cloud optimized geotiffs because it really democratizes the access to satellite imagery. Somebody like me who doesn't have anything but time and interest and motivation can get access to this and start doing new things without needing huge access to upfront capital. So for example, all the demos that I've shown, not a single thing uses a third-party service other than my own Amazon Web Services compute that takes data from S3. So now I want to talk a little bit about advice if you're using this, using cloud-optimized geotiffs and mosaics in your own projects. So I talked previously about Landsat and how the flexibility is amazing because it allows you to see different temporal differences. Well, that flexibility is also really difficult to work with. Historically, you would look at one Landsat scene at a time, which is easier to work with because you don't have to figure out how to merge different images. With NAIP and elevation, working with this mosaic, creating a mosaic of lots of different images is relatively easy. NAIP is designed to be, it's taken at the state level, none of the images overlap. There's no seasonality, there's no cloud cover because it's taken specifically to minimize those differences. But with Landsat, it's really hard because you have so much variation among Landsat scenes. You have difference in cloud cover, you have summer and winter images, and you don't want to combine some Landsat images that are cloudy in the summer with other Landsat images that are cloudless in the winter. It wouldn't give a very good analytic representation of the data. So I've been working on tools to combine these into a mosaic that that tries to preserve some of these differences and minimizes the amount of clouds while also minimizing the temporal variation within a mosaic. Similarly with historical maps, it's pretty hard because there's very different scales and resolutions and temporal variation. I want to talk a little bit about performance because this was one of the things that I was highest on my list when I started with this. When I got my first Landsat mosaic working, it took 15 seconds for each tile to load, which is not acceptable in the browser. Over time, I profiled and found that the number one thing that determines performance is the composition of your mosaic. So here on the right, you can see that these are the placements of each Landsat scene. And as you move up towards higher latitudes, the number of overlapping Landsat images per Mercator tile increases. If you include lots of different images in your mosaic JSON, which is a mapping from Mercator tiles to cloud optimized geotiff files to combine into one image. If you include more and more source images, it takes longer and longer and longer to make the final image that you send back to the browser. So I've worked on a project, an open source project that analyzes the placement of these scenes and analyzes the Mercator indexing system to find the fewest possible Landsat scenes that are necessary for each Mercator tile. As I noted before, by parallelizing bands, I can make the feeling that when you visit the website, it's very fast to load because the Landsat is parallelizing these requests. And I've been able to get Landsat average latency to 1 second, which is when you load the website within, as you're panning around, new images should load within a second. And for NAIP, it's about 500 milliseconds. A bit about pricing that because I'm using a serverless architecture, it's an extra reinforcement for why I should focus on performance, because the less time that your Lambda function runs, the less you have to pay. So I've gotten some of these down to pretty cheap in terms of NAIP for $30 per million request is pretty cost effective. As a comparison, I believe that Mapbox for their raster images, once you pass their very generous free tier, is like $250 per million requests. Landsat's more expensive because there's more images that you have to read for each Landsat request that you send back to the browser. But these are rough numbers that correspond to the prices that actually reach your server. And if you cache, you can make it even cheaper. Especially with Landsat, when you cache each band individually, it allows for cheaper serving, because if somebody looks at NDVI and then looks at EVI and then looks at false color infrared, you're only sending that data once. So thanks to USGS and USDA and AWS and others for putting this data out there. That I'm really excited about its potential to democratize access and allow people like me who don't have the resources of a company, at least when I started these projects, to do cool things. All of the things that I've mentioned are open source on GitHub. I've added links in the presentation. I hope to upload this presentation to wherever I have to after soon. Yeah, I'm open for questions.
Kyle, wonder if you have, this is Rich, wonder if you have could you just do a 1 minute live demo just to show the performance of something? Because slides just, don't quite do it,
I know,
I mean, it was awesome. It was an awesome talk, but it's so cool to see
Give me 1 sec to share my screen. I was trying to do GIFs, but it's a little hard it was a little hard to do really nice GIFs. So for example, here I can change the presets, and there's new data coming in. I can change the color map that I apply. I can change the index, and it's all quite fast because it's downloading in parallel. It's a little slow to change to 3D. There's some performance improvements that I want to make, but it's usable. There's some things that I want to do. Definitely some performance improvements that can happen in the future, but exciting. Here with NAIP imagery, it's as you move around, there's a cold start, which the first time you request images from AWS Lambda, it's a little slower to load while it starts up. But then as you move around, it's really quite fast to load. And you can select, I want to see imagery from 2014, or I want to see imagery from 2011. And because everything is coming from cloud optimized geotiffs, it's incredibly fast to load and cheap as well.
Awesome. And I just want to say, since I'm from USGS, I just want to say it was so cool to see someone who wasn't funded by USGS develop something, out of this data that, just blew a lot of people away. And that's the whole point of this cloud optimized, analysis ready data, right? Is that anybody can build anything, so many possibilities.
Yeah. Well, thanks.
Yes, thanks a lot, Kyle. That was that's a great showcase of the different things that you can do with cloud optimized formats.
Thanks.
Are there any, let's see, Annie was doing this before. I think I have it up. Were there any questions? I think we can, well, we want to make sure that Scott has enough time, so maybe we should skip to him.
Yeah, we can have questions after Scott as well, I'm sure.
Okay.
Sounds good. However you want to do it, Matt.
All right. Yeah, let's get over to you, Scott.
All right. Can everyone see the slides? Just checking. Okay, great. Well, thanks everyone for attending, and thanks Matt for the opportunity to give this presentation today. I'm Scott Henderson. I'm a research scientist. I work at the University of Washington eScience Institute, and I'm a research scientist in the Department of Earth and Space Sciences as well. So today I'm going to talk about integrating STAC catalogs with open source infrastructure and open source software used in earth science research. So coming at this from the perspective of a researcher using remote sensing data. There is a link to these slides that's pretty easy for folks if they want to follow along too. bit.ly ESIP intake STAC. So the title of this talk was mentioning Pangeo. Pangeo is a community that I've been involved in over the last year that is promoting open, reproducible, and scalable science. So this involves developing both open source infrastructure as well as and software, as well as fostering communication between software developers and scientists. And so a big part of this project is just running forums and facilitating communication between folks. There's a session on Thursday that's actually going into this effort in detail. So I'll hold off on more details, but I encourage folks to check out that session and also the website at the top of the slide here. So my particular involvement in this project started a little over a year ago, funded by a NASA Access grant. And I've been able to work with a great team of people that spans both industry and academia. So these are the folks involved in that grant. And this grant is really focused on leveraging a lot of the open source tooling that Pangeo has been developing, with particular attention to NASA datasets as they move towards cloud storage. So storage on AWS in particular, but other cloud providers as well. So what does this kind of open computing infrastructure look like? Trying to distill the infrastructure in one slide here. And I'll show some examples later in this presentation. But the key idea behind this project is moving algorithms to data rather than the common workflow of finding and downloading data to laptops. So you can kind of start actually on the right-hand side of the screen here, where a user is happily interacting from their laptop via a web browser to interact and analyze data sets sitting on a cloud or HPC system. So many scientists, software engineers, just people in general working with any code and analysis are very accustomed these days to Jupyter notebooks. And the ability to run a Jupyter server on different systems allows you to have that same user interface. So running Jupyter notebooks in a web browser, but the actual computations can be happening not on your laptop, but in fact, in the data centers, wherever your large amounts of imagery sit. So the key is moving more computations next to data. And also, in contrast to operating on your laptop, you have the huge advantage when you're operating in cloud environments to be able to scale your computational resources dynamically. So we heard a little bit about Lambda processing on AWS. In this project, we've been using Kubernetes as kind of what's happening behind the scenes on cloud providers that gives us the ability to launch additional machines, giving you access to more CPUs and more RAM or GPUs on an as needed basis. So that works because of integrations with the Dask library, which is a Python library for distributed computing. I'll go into that in a little more detail in a bit, but we've put a lot of emphasis on Python packages, open source Python software that really works well together to do scientific computations on remote sensing data sets. And I want to mention as well, this system is all predicated on the data being in a good format for cloud storage. So there's no perfect solution here, but some formats we've been exploring are ZAR, which hasn't been talked about today, but is sort of a drop-in replacement for HDF when you're putting things in cloud storage like AWS S3. We've heard a lot about cloud optimized geotiffs, COGS. There are other formats out there as well, like TileDB, that people have been exploring. And we want those data sets to be cataloged in some way for them to be discoverable. And so I'll advocate for STAC in this talk for that catalog. So that is the infrastructure overview. And sitting on that infrastructure is a collection of Python libraries. It's very flexible which of these Python libraries you put together to work with your data. On the last slide, we saw 3 kind of mentioned. There's Jupyter kind of orchestrating the whole show, Dask and X-Ray for interacting with raster data. I'm also going to emphasize Intake and HoloViz Python libraries today. So what led me to discovering STAC in this project is we initially set up this Jupyter, Pangeo Jupyter infrastructure on AWS and wanted to work with data in the cloud regions where we set that up. So the AWS registry of open data is fantastic, kind of laid out all these available data sets, some in COG, some in other formats. But at least a year ago, there was sort of a mishmash of formats and metadata, and to actually open or download files required kind of constructing URLs, knowing, for example, what Landsat path and row you're interested in, rather than doing geographic searches like we might be used to on a NASA Earth data search system. So about a year ago is when I came across STAC, and just the mission really resonated, seeing this wide variety of data sets that were starting to appear on cloud storage. There seemed to be a need to develop a standard and gather community support behind a simple metadata standard that could help facilitate access to all this data. So I first came to STAC because I was generating thousands of radar scenes for my own research and doing this on AWS, and wanted to share these results with other scientists that I was collaborating with. So I wanted to create a simple set of metadata and then have some sort of simple way to share these results, since everything theoretically would be easy to share sitting on web-enabled storage. So the great thing about these open standards is you combine them with open software and the benefits just cascade. It's very little additional effort for you to use the web browsing capabilities that other people produce. You just have to generate a compliant STAC catalog. So unfortunately, I'm not sure this video is going to play. Let me just check real quick here. Well, I don't know if people can see this. It's quite small. Maybe there. So the STAC browser allows you to, given a STAC catalog, interactively navigate it. So I'm just marching through JSON files, which Matt showed us earlier, where we get radar images displayed in this interactive view. So when I came across this, this really felt magical to me because I'm not a web developer, but I was able to simply put together some bounding boxes for the files I was generating and then have this pretty fantastic website to share with other collaborators. Here's another view of this STAC browser. This is a more recent update looking at Landsat data. Now you're able to, as we've seen in other examples, select different bands. You could change color mappings. And as you zoom into these tiles, you get the resolution updating behind the scenes using some sort of dynamic tiler, whether it's on AWS Lambda or some other system, but this is great. So, but there is one drawback, which is that this is really still a visualization tool. And I often want to extract these underlying arrays and do some sort of custom computation with this imagery. And so the question we were asking once we started to see these tools was, could we replicate this same experience from within a Jupyter notebook and give access to kind of more computational workflows, arbitrary computational workflows. So that is where the intake library comes in. Intake is a Python, open source Python library that's meant to facilitate working with data, loading data into Python objects, keeping catalogs of objects. It's not specific to STAC or cloud optimized GeoTIFF. You could use this same system for a catalog of CSV tables or HDF data sitting on an HPC system. It's very flexible. So it's more of a framework really to think about how to organize data. And these bullet points kind of touch on what exactly it provides as a framework. So I want to focus mostly on intake stack. There are various kind of plugins you can attach to intake depending on the data you want to work with. And so intake stack library is something that started out of this project about a year ago. And it's still very much being developed. But the key idea was to take existing stack catalogs and use intake to get these data sets into Xarray, so into a Python environment for analysis. So the option one is you have your stack catalog and you have this JSON metadata file that points to, for example, all the Landsat bands in cloud optimized GeoTIFF for a specific acquisition. So in this case, you still need to know the URL to where that metadata sits. But given that URL, you can create a driver that allows you to open that Landsat acquisition. And then you have a simple syntax to extract a given band and load it into an Xarray object in Python. So Xarray gives us this very intuitive interface for working with multidimensional data where we might have latitude, longitude, time, or UTM, eastern, northern band number for any given Landsat acquisition. It's also connected to this library Dask for parallel computing. So on the bottom right here, which got a little cut off, you can see the representation of this array where we can specify how we want to deal with the tiling and how we want to send chunks to distributed computing workers, whether they're separate machines or multiple cores on a laptop. So this sort of brought everything together, I would say. Once you've loaded things into Xarray, then you have the entire API or all the functionality of Xarray at your disposal. So you can do band statistics, subsetting, extracting specific ranges of the data sets, custom mosaicing. Kind of the sky is the limit because you have access now to underlying data and any Python libraries you want to use. You can also do interactive visualization, which with a library called, well, a collection of libraries under the Holoviz title. So this is picking a particular band. And unfortunately, this isn't a screencast here, but as you zoom in, you are fetching the appropriate resolution from the underlying cloud optimized GeoTIFFs for a given band. So where things really come together is using this an API for searching the stack catalog. So Matt mentioned Earth Search earlier. So this is an API that's set up to search various stack catalogs that exist, such as Landsat. And now the user interaction is kind of what we want as a scientific community, where we're interested in a specific place, a specific time, and maybe some additional metadata properties that we want to search on. So we can search for Landsat data for a particular bounding box, time range, and then open the results of that search through intake. And we're no longer dealing with like the underlying URLs to where those files actually reside. It's just the search. And then we can use some features built into intake, like their graphical user interface, to browse those results interactively. So here we're looking at the Landsat frames and maybe the bands or thumbnails available per Landsat acquisition. There are also these convenience functions that you can build into the intake library. So this really facilitates common workflows, such as constructing more complicated data cubes, as we've seen earlier. Maybe you want to do band, you want to do a custom band index or some sort of calculation using not just a single band. So you can put together functions that are built into the system for whatever those tasks are. So this is an example here of creating a multidimensional data set where we're asking for specific bands in a Landsat acquisition from the intake catalog. We're definitely working on improving this user interface, because another set of convenience functions you can do is specifying what kind of plots you want to have come up by default. So maybe it's an image with a particular color mapping, log scales, maybe it's a histogram for whatever data sets you're working with. That's fairly easy to do. So this user interface explorer is kind of built into intake. So we did not, as this project, put anything into this code. Just by mapping the STAC catalog to the system, you inherit some of this functionality. So that's why it's really nice to connect all these open source projects. But effectively, what you have once you start doing things like this is that STAC browser experience, but from within a notebook, where you're interactively browsing this imagery, but you can pull it very easily into a Python X-ray object and then do whatever computations you might want to do. So this session kind of had an emphasis on scaling things to larger sets of data. This is a link to an interactive demo where we're constructing a more complicated X-ray data set. So in this case, this is a 75 gigabytes of Landsat data for 19 acquisitions, and we're kind of separating things out in terms of the common name band index for the data variables in this data set. So this example is nice because it brings together all these tools I've mentioned. It does distributed computation using the scaling DAS cluster to calculate a band index on this particular data set here. So you can go to this link later and run that and check it out. There we go. Some future effort that we're interested in is connecting NASA's Common Metadata Repository search results with STAC compliant outputs. And so if that's the case, you can imagine as long as you have these results from a STAC API type search, you can load whatever those data sets are into Python. So this would work best when things are stored on S3 with the easy accessible format like a cog, but it doesn't have to be. It could be sitting at on a different server at a different location. But you can reuse this machinery starting from STAC to easily ingest data without having to know what the URLs for downloading or directly addressing data files are. I think I'm a little over time, so I just want to end by saying one of the great aspects of this Pangeo project is we've put a lot of emphasis on opening up interactive examples. And so if you go to this website, gallery.pangeo.io, you can use these binder buttons to launch interactive notebooks where you're running Jupyter and you're able to experiment with this code code's pretty hard to look at in the presentation. So I really encourage people to do that. It's been supported very generously by credits from AWS and Google Cloud. But we'd love for more people to get involved in the intake stack development and try out these demos and see for yourself kind of the state that things are in. So thank you.
Thank you so much, Scott. We only have 5 minutes. I don't know if is this the same room that's used for the next session? Yeah. Any questions? There's a few on Slido. Everybody would be encouraged to go to the polls on Slido and put in your 3 takeaways for the session. It looks like Rich has asked a bunch of questions. Rich, what are the most important questions?
Well, actually, one was just, could you do a STAC query and generate one of those Mosaic JSON files, or is that a dumb thing because there's no real need to do that?
There was some talk I remember talking about this with Vincent and Sean at DevSeed, and at one point they were gonna suggest an extension to STAC to sort of facilitate that. But yeah, I'm not even sure if it's really necessary. Kyle, do you have?
Yeah, so I've also been talking with Vincent, and I think it's definitely possible. So I haven't been using STAC because I'm generating global mosaics that are more static, but I want to allow somebody to visit my site and say, I want to see this Landsat data between this date and this max cloud cover. And for that, I would use STAC. I think the issue that is referred to is that there's an extension to STAC that could make it easier to use on the fly with Mosaic JSON.
Yeah, I think there's just some missing information that we sort of need to sit down and figure out what that is and get that added. And I'm more than happy to do it. It's just, yeah, I think that definitely that was a good question, Rich. That would be really cool to be able to do that. Any other, I think Ed asked a question here about linking to external records. So I don't know if I really did answer it, but you can, so in STAC, as one of your assets would be the original metadata. So you could link to whatever it is that's important. So all of that would be self-contained in the STAC record. It would point to all of the pertinent information. Any other pressing questions?
Yeah, I was just going to ask quickly. So intake is built on top of STAC, right? So is there? So I mean,
yeah. So
the connection with
intake is a separate library for generic data loading, and then intake STAC is like a plugin sort of to that, based on STAC.
So with intake STAC, we can do almost anything that we can do with STAC.
They're totally separate, and so the intake stack is just facilitating loading data into Python that's referenced in a STAC catalog, but you can put them in totally separate categories.
So just by using intake, I'm not using anything from STAC, right? I mean, that was my question.
That's right.
Right. So hold on a second. Yeah, and just as an aside, I mentioned Open Data Cube before. So Open Data Cube is actually, it's kind of a similar type of thing as what Intake STAC is doing. It opens up the data in X-arrays and allows you to access it. Open Data Cube requires you index everything into a database first. So you can take STAC, you index all of that into a database, and that's what is referred to as the Open Data Cube in PostGIS. Intake STAC doesn't require that, so that's nice. But but Open Data Cube has some additional features. But they're similar in what they're trying to do, which is go from the original data to create multi-dimensional arrays, and you'd be able to use X-arrays in order to scale things up.
Could you implement Open Data Cube, you know, through these tools without the need for that database?
That's a good question. I think you can. I think it's really certain features in Open Data Cube that do like reprojection. Like there's a lot of like magic that can sort of happen. So you could do it. I just don't like. You're not necessarily doing reprojection like when you open up, let's say, multiple Landsat files and they cross UTM zones, right? Like you'd have to really take care of that yourself. Whereas in Open Data Cube, it doesn't matter what the projection is, and it will do that automatically.
Do you mind if I take 30 seconds to answer a question? There is a question in the Slido saying, does the client-side GPU rendering in my talk require a specific library and GPU hardware type? So I use DeckGL, an open source library originally created by Uber, and then this spring was put into open governance. It's now under the auspices of the Linux Foundation. And that's, I'm leveraging that for rendering on a map, basically. And then I can add specific GPU code under that, but it will work on any device with a GPU or any device at all. Even if it doesn't have a dedicated GPU, it'll still work.
Cool. Well, it sounds like, so this room is actually open, so I'm happy to stay around for a few more. I do want to go to room 5 for the other cloud optimized session, which is being run by Patrick Quinn of Element. And there's going to be some cool talks in that. So if this
That starts at 4 though, right?
Yeah. Oh, it starts at 4?
Yeah.
Oh, look at that.
I'm gonna end the live stream for the session in this room so we know where to lop it off. But yeah, so this Zoom, if people want to hang out and keep talking, this Zoom can stay open for the rest of the day. But yeah, the next session does begin in 30 minutes over in room 5. So I'm just gonna stop the live stream for now, but continue to chat if everyone would like to hang out. And remember to add your 3 takeaways into the Slido poll. You can see that people added that link to chat.
Great, thank you, Annie.
Mm-hmm.